Hello world, I'm Sarah Matthews, and in this video I'm going to be walking you through how to pre-process your monochromatic astrophotography data using PixInsight to get to your final master light files. Now we are going to be taking a little bit more of a hands-on step-by-step approach here rather than using an automated script like weighted batch pre-processing. And while yes, I do love that script and it is always evolving, I know that sometimes us imagers just want to be able to have a little bit more control over our processing workflows, as well as just want to have a better understanding of the processes in general. So without further ado, let's dive right in. Alright, let's begin our adventure to create our master light files for the North American Nebula. So by the end of this tutorial, we will have a total of 3 master light files, one for each filter that I use with my monochrome camera while imaging this target. So one master light file for hydrogen alpha, one for oxygen 3, and one for sulfur 2. Now all the concepts I'm going to be going over will be applicable for any type of filter that you may have used with your monochrome camera, so any narrowband or broadband filters or any combination of the two. I just happened to image this target only using these 3 narrowband filters, but the concepts I'm going over are going to be applicable to all. Oh, and also, if you are interested in how I post-process the 3 monochrome images to create this final color image of the North American Nebula, check out my YouTube video. I've posted a link to it in the description box below if you want to check it out. So here we are in PixInsight. I am running version 1.8.9-1 at time of filming. Let's head over to our folder with our data real quick so I can give you a quick rundown of that. So I have an overarching folder for all of my data for the North American Nebula that I acquired in 2022 right here. I've organized that data into folders by subframe. So here I have my lights of the North American Nebula and I have them organized by filter type. So here are all of my hydrogen alphas, here are my oxygen 3s, and here are my sulfur 2s. They are all 300-second exposures or 5-minute long exposures taken at a gain of 100 and binned 1 by 1 with the same relative temperature as well. Now, if I had light frames that were taken at a different exposure length than 5 minutes or taken with a different gain or binned differently, I would make separate folders for those frames and process all of those with their own respective calibration frames. That's very important to remember. But speaking of calibration frames, I have 3 different types. I have my darks right here. They're all 300-second exposures, so 5 minutes long with the same gain, binning, and relatively the same temperature settings as my light frames. I also have my flats here in this folder. Since I took HA, O3, and S2 light frames for this target, I also took flats for each of those filters and organized them into subfolders by each filter type. I believe I have 60 of each. Next we have our dark flats right here. I have taken dark flats for each filter that I took flats of, using the same exposure time as my flats with the same gain, the same binning, and the same temperature settings that my flats had. And they are all organized by filter type, as you can see. Really quick, before we move on, if you are using a dedicated astronomy camera that is cooled, or in other words, where you can control the temperature of your camera, you can create a library of master darks and master dark flats, so you don't need to take them for each target that you do. As long as the darks match the exposure length and temperature as your light frames, you're good to go. And as long as your dark flats match the same filter type, exposure length, temperature, etc. as your flat frames, you're also good to go. You can do the same with bias frames if you prefer to use those as well. However, for the purpose of this video, I'm going to be organizing my files like this just because it makes it a lot easier. But yeah, speaking of bias frames, I know some folks prefer to use bias frames in place of dark flats. So if you'd like for me to do this video but with bias frames, just let me know down in the comments. The process is very, very similar. Yeah, last but not least for my folders, I have a PixInsight folder that I will be placing all of my files that we are going to create through our pre-processing workflow in here. I highly recommend making a folder for this because it's just going to help for organizational purposes. So first things first, we need to visually review our light subframes. We will be using Blink for this, so come up here to process, all processes, down here to Blink. It looks like this. So I'm going to be reviewing my light subframes by each filter type. I do also review all of my calibration frames as well, just to make sure I didn't mistakenly include a calibration frame that was bad or was misorganized or named incorrectly. I won't do that for this video. It's just a recommendation I'm making. So let's load in all of our raw HA light files first. So let's come down here to this folder. So I have it in here under 2022, lights, HA. So I'm just going to select all, bring those in. So all of these have an auto stretch applied to them so we can see what we're working with, but they are very much still in their linear state, which is a good thing. So in this first image evaluation step using Blink, I'm mostly looking to make sure that all the light frames are of the target and that I didn't mistakenly include an incorrect file somehow. I'm also looking for frames that have any visually obvious defects like star trailing or considerable cloud coverage, etc. So I'm going to go through each frame. I'll uncheck the ones I want to delete later or will be moving into a new separate discard folder that will be discarded later and won't be used. But for frames that have airplane and satellite trails in them, generally I keep those in the bunch as long as they don't have any of the other visual defects I just mentioned, because generally those trails from satellites and airplanes will be removed during the pre-processing stages, so don't worry about them too much. So let's start with number 4. I had to delete 1 through 3 because I took those at a gain of 0, so couldn't really use those. Let's just go through those. I'm just going to be using the arrows on my keyboard. Actually, yeah. So this looks good, 5 looks good, 6 looks fine, 7's fine, 8. So here is a star trail, or here's a satellite, I believe here, satellite trail. 10 looks fine, 11 looks fine, 12, oh, that's cool. Alright, so I didn't see anything that was visually defective in any of these images, so I'm going to keep all of them. So let's load in all of our 03 frames so I can show you kind of what I'm doing. So just select all of these and then come down here to close the selected images and come over to the folder here and let's load in our 03s. 03. Alright, so again, yes, they are in a linear state. I've just applied an auto stretch. So 1 looks fine, 2 does, 3. Okay, so this is what I'm talking about. We don't want this, even though it looks pretty cool, we don't want to keep that, so let's just uncheck that. Number 6, and number 7, and 8. Okay, 1 looks good, 2, 1 again is good. Actually, let me check why, that's okay. Alright, so we have deselected 3 of the images for 03, so let's select all the ones that we are not going to keep. So let's move them. So let's come down here and click on this little icon button here to move them into a new folder. So in the 03 lights folder, I'm just going to create a new folder called discard, 03 discard. You can call it whatever you'd like. Okay. And then I'm just going to close those selected ones, and then the remaining ones I'm just going to highlight and then move over in, or actually I don't need to move those over. We're good. Okay, so let's just highlight these and close those and bring in S2. Alright, so here are our S2 light frames, and yes, they are in a linear state, they just have an auto stretch applied. So let's start with number 1. So we don't want that one, don't want that one, or that one, or that one, or that one. Wow. Okay, so let's highlight the ones we want to get rid of and move those over into a discard folder under S2. You might be wondering why I don't just delete them right then and there. It's because sometimes I've made a mistake and put an image I didn't want to put in there, so I just do that after the fact. Alright, so let's close those ones, and these are the ones that we're keeping, which is good. Alright, so now that we have reviewed our HA, O3s, and S2s and have discarded the ones that have obvious defects, we are going to move into the calibration portion of this video. Now that we have reviewed our light files and have what we need, next we are going to go over calibration. Now, as you all probably already know at this point, calibration frames like our darks, our flats, and our dark flat frames are all going to come together to help create final master light files that are free of artifacts and have higher signal to noise ratios. So to do this though, we actually need to create master files for each type of calibration frame that we have. So for example, in this case, since all of my light frames were taken at the same exposure length of 300 seconds with the same gain of 100 as well as the same binning and same temperature, I need to create one 300 second master dark file. Then I need to create 3 master dark flat files, one for HA, one for O3, and one for S2. And then I need to create 3 master flat files, one for HA, one for O3, and one for S2. So altogether, we are going to be creating 7 master calibration files in this video. And the reason we need to do this is because if we were to calibrate our light frames with all of the individual calibration subframes that we took, it would actually end up causing more noise in our master light files, which is not good. And it's also beneficial to create these master calibration files because what they do is they end up creating statistically better sampling of our camera's output. So overall, doing this is just a bigger win. So here's a high-level overview of how the calibration process is going to work. So in step 1, we are going to be creating our master dark file. So we're going to create one master dark file. Since my light frames were all taken at the same exposure length of 300 seconds, and all of my dark frames were also taken at 300 seconds as well, I need to create one master dark file by taking all of my 300 second dark sub-exposures and integrate them into a single master dark file. Next, we will create 3 separate master dark flat files for each filter that we use to create our flats. So one master dark flat file for HA, one for O3, and one for S2. Third, we are going to calibrate our flat frames by filter type. We need to calibrate our flat frames before we integrate them into master flat files because they were taken in an illuminated environment, whereas our darks and our dark flats were taken in complete darkness. So no calibration is needed for those. Once I have calibrated my flat frames, we will create 3 master flat files, one for HA, one for O3, and one for S2. And then our 5th and last step in calibration is to calibrate our light frames. So after these 5 calibration steps, we will move on to the next steps in our pre-processing workflow. So here's a high-level overview. So after the calibration steps, we will move into cosmetically correcting our calibrated light frames, and then we will move into grading our calibrated and cosmetically corrected light frames in SubframeSelector. And then after that, we will take the calibrated, cosmetically corrected, and graded light frames, and then we will register them in StarAlignment, and then we will do some local normalization, and then we will integrate them using ImageIntegration and DrizzleIntegration to create 3 master light files for HA, O3, and S2. So step 1 in calibration, we are going to be creating our master dark file. And this master dark file will be made up of the 300 second dark sub-exposures and be used to calibrate the 300 second light sub-exposures. Now, if I had light frames taken at different exposure times, I would want my darks to match that. I'll touch more on this a little bit later, but to keep things simple, make sure that the exposure settings match your light frame settings. It just helps a lot. So to create our master dark file, we are going to be using the image integration process for this. So come up here to process, all processes, over and down to image integration. It will look like this. So I'm going to just reset it down here just for good measure. This is a good thing to do. You can also save process icons as well, but I'm not going to get into that in this video. So the first things first, let's input our images. So let's add our dark frames. So add all 50 of those. Let's just double check to make sure they are all darks. Brilliant. All right, so for formal hints, I'm just gonna leave this the same. So under image integration for combination method, first I'm going to keep this at average because average is always going to create a master file with the highest possible signal to noise ratio just across the board. For normalization, I'm gonna use no normalization. We don't need to normalize for any gradients like that because it's a dark frame or they're dark frames. For weights, select don't care. We aren't worried about how to weight our dark subframes like we are with our light subframes. Make sure that generate integrated image is selected. You can keep everything else the same. Under pixel rejection 1, you need to select a rejection algorithm. I generally select linear fit clipping, but this is going to be based off of how many subframes that you have, and if you hover over the rejection algorithm portion of this process, it'll give you a list of options to choose from. So typically linear fit clipping is going to be good for 25 plus frames. Windsorized Sigma clipping is going to be good for 15 to 25 frames. Average clipping is going to be good for 7 to 10 or more frames. Percentile clipping is good for fewer than 7 frames. So I'm going to be selecting linear fit clipping. And then for normalization, select no normalization again. Deselect generate rejection maps. We don't need that. You can keep everything else the same. And then I like to just keep everything else the same. And then just come down here to the circle and apply global and let it integrate. Alright, we are finished, so let's review it. Just come over here and do an auto stretch by clicking on this little guy here. Looks good. Alright, let's save this. Come up here to File, Save As. So what I'm going to do is come over to that PixInsight folder and then create a new folder inside of that and call it Master. Press Create, and then I'm going to call this Master Dark 300 seconds. And then I'm going to save it as a .xisf file. And press Save, and then I'm going to save it as a 32-bit floating point one, and you can keep everything else the same. Alright, and we are good to go. We can close that. And then we are going to move on to our master dark flats. Okay, so next on our list is to create 3 master dark flat files. One for each filter that we use, so one for HA, one for O3, and one for S2. So the master dark flat files we create here will be used to calibrate the flat frames in step 3, which is the next step in our calibration workflow. So now we will be using the image integration process again for this, so if you have it open still, click here and reset it, or just come back up here to process, all processes, and then find it down here, image integration. So I have reset everything. So I'm going to add my files. So let's go over to dark flats. Let's start with HA. Let's load all of those in. I have 30 of those. So let's just check, make sure that I have all of my HAs. 5 in my filter wheel is HA. So if you ever see 5, that's what it is denoting. So it looks good there. Formal hence, keep that as the same. So for image integration, keep it at average again. For normalization, just like we did with darks, it needs to be no normalization. And then for weights, we also need it to be don't care at all. The settings here that we're going to go over are going to be the exact same that we did for our darks. Keep that selected. You can minimize that. Pixel rejection, since I have 30, I'm going to do linear fit clipping again. You can just hover over the rejection algorithm and a list of the best options will appear based off of how many you have. For normalization, select no normalization again. You can deselect generate rejection maps. You can keep everything else the same. And then I'm going to keep everything else here as is. So just apply global. All right, so we are back. Let's take a look at it. So come up here and do an auto stretch. Brilliant. Let's save this puppy. So come up here to File, Save As. And then we're going to save it under that PixInsight master folder. So let's call this Master Dark Flat HA. And we want it to be an XISF file again. So press Save and then keep it at a 32-bit floating point. Okay. So we can close that. Now let's clear out all of our HA files and load in O3, and we are going to repeat this process for O3 and S2. So clear the HA, and let's load in our O3s. Again, I have 30 O3. Alright, so we have our O3s loaded in. Let's just make sure that we have all O3s, and they should be all number 6s because in my filter wheel, 03 is designated as number 6. And then we can keep everything else that we put here the same. In particular, the rejection algorithm, because we have more than 25 frames, we can keep it at linear fit clipping. If you changed however many you have here, then you would need to update this, but everything else can be left the same. So let's apply global. Alright, so 03 looks to be done. Let's take a peek at that. Brilliant. Let's save it. Save as. I'm gonna do it again under the PixInsight master file folder. It's called master dark flat 03. Of course, you can call it whatever you'd like. Save. Alright, let's close that and let's bring in S2. So all we need to do is clear the 03s and add in S2s. So let's just double check to make sure that they are all S2s. For me in my filter wheel, S2 is number 7 in the filter wheel, so it is designated as number 7. So looks good. Cool. All right, and I have 30 dark flat frames for S2 as well, so I don't need to change the rejection algorithm. So we'll just keep it at linear fit clipping, so we can just apply global. All right, so our S2 dark flat frame is ready to go. Let's take a peek at it. Come over here, auto stretch. Looks brilliant. Let's save it. File, save as. Again, under PixInsight master, let's call it master dark flat S2. Save. We are good to go. Now let's head over to calibrating our flat frames. Alright, so we are now on to step 3 of our calibration workflow, and we will be calibrating our flat frames by filter type. So just as a reminder, we do need to calibrate our flat frames because they were exposed to light, so we will be doing the calibration before we integrate them into master flat files. And the PixInsight process we will be using for this is called image calibration. So let's open that up, come up here to process, all processes, down here to image calibration. So it looks like this. So we are going to be doing them by filter type like I said, so let's add our HA files first. So let's go into our flats, HAs, and I believe I have 60. It's a little bit excessive I guess, but I'm just gonna do those 60, press open. Let's double check to make sure all of them are HA. Again, in my filter wheel, HA is denoted as position number 5, so that's why you see this 5 here. So let's just make sure that they are all 5s. Okay, cool. So next, you can disable CFA. We are using a monochrome camera, not a one-shot color camera. If you were using a one-shot color camera, you would want to keep that enabled. For formal hints, you can keep this the same. Okay, so we are going to be creating a output directory for our calibrated flat frames. So we need to create one. So let's select the output directory little icon here. And under our PixInsight folder, let's create a new folder called Image Calibration. You can call it anything you like, calibration or whatever, but I just like to use Image Calibration. So create, and then we're going to create one for flats, since we also will be calibrating our lights. So here's the one for flats, and we will be doing it by filter type. So let's create this one for HA. So that looks good. So it should be here. And what you're going to see as the flat frames are calibrated is you're going to see an _C in the file name, and I'll show you that in a second when they are calibrated. You can keep signal evaluation and noise evaluation the same. Down here under overscan and input pedestal, you can keep everything else the same. For master bias, uncheck master bias because we're not using a bias frame or master bias frame. And then we are going to be using a master dark, so keep that checked. And we're going to be using the corresponding master dark flat file we just created in step 2. So for HA flat frames here that we have loaded in, we need to use the master HA dark flat frame. So let's load that in now. So come over here to this folder icon, come over here to PixInsight under masters, And let's find that master dark flat HA file. Select open. Okay, so we don't need to calibrate and we don't need to optimize either, because our exposure settings for the dark flat frames are the same as the flat frames as in exposure length. So if you had differing exposure lengths, say for instance you had a dark flat frame that was of a longer exposure time than the images that you were calibrating, you could use the optimize feature. So, but I'm not going to do that, so I'm just going to deselect that. We don't have a master flat, so you can deselect that, and let's just apply global. Alright, so our HA flats are done being calibrated, and like I said, they were put into a output directory that we created. So this output directory, let's go into PixInsight, image calibration, flats, HA, and here are those calibrated HA flat frames, and like I said, they will be designated or denoted with a _C to represent that they have been calibrated. So we can close that. Now we are going to do O3 and S2, so we are going to be using image calibration again, so let's just clear out the HA flats and add in the O3s. So let's go to the flats, so flats, O3, load these all in. Again, I have 60. Alright, so that looks good. So let's make sure that all of these are O3s, and in my filter wheel, O3 is designated as the number 6 position, so that's why these are listed as 6. So let's make sure I have all of these are 6s. Good. Okay, so for output files, we need to change the output directory to O3. So let's create one. So again, it's going to be under that PixInsight folder, and then under image calibration, and then flats. So under flats, let's create an O3 folder for our calibrated flat frames. That's where they are going to be stored. Can keep everything else the same, We are going to want to change this master dark to the corresponding master dark flat O3 frame. So let's open up that. So come up here or down here to PixInsight, master dark flat O3. And they have all the same exposure settings. So I'm going to keep everything else the same, and let's apply global. Alright, our O3s are done. Let's look them over. So here they are in the folder. All 60 of them with the _C. So let's move on to S2. So let's clear out O3 and add S2. Flats, S2. Again, I have 60 of them. It's a bit excessive. Probably get away with 30. So let's change the output directory to image calibration flats S2. So let's go under PixInsight image calibration flats and create our S2 folder. Good to go. Okay, keep everything else the same. You're going to want to change that master dark flat though to the master dark flat for S2. So come over here to PixInsight, master dark flat S2, and then press apply global. Okay, so our S2 flat frames are done being calibrated. Here they are in the folder that we just created. So we are good to go. Now we are going to create 3 master flat files, one for HA, one for O3, and one for S2 with our calibrated flat frames. Alright, so we have all of our flats calibrated. Next we need to create our master flat files like I mentioned for each filter. So again, we're going to create one master flat file for HA, one master flat file for O3, and one master flat file for S2. So we will be using these master flat files in the next step when we calibrate our light frames. Now to do this, we will again be using the image integration process. If you don't have it open up already right here, like I've saved it, again, just come up here to process, all processes, image integration. It's right here. So we reset these settings, good. Now we need to adjust the configuration settings, and they will be different from the settings that we use for integrating the dark and dark flat frames, because again, these flat frames have been calibrated because they were exposed to light when they were taken. So let's load in the HA flat frames first, the calibrated HA flat frames. So let's come up here to add files. Okay, PixInsight, image calibration, flats, HA. So again, these are all calibrated. You can see them denoted with the _C in their file name. Just going to highlight them all. 60 again is a little excessive, but that's fine. So let's double check to make sure they are all HAs. So that's number 5 for me in my filter wheel. So we're good to go. Cool. Formal hints, you can keep the same. Image integration, keep the combination as average, because again, that's going to yield a higher signal to noise ratio final image. So for normalization, we're going to select this one. I have a very hard time trying to say it out loud, so just choose that one. For weights, we're going to choose don't care at all for all weights equal 1, and then keep generate integrated image, and then we can minimize that. For pixel rejection, for the rejection algorithm, I'm going to do linear fit clipping because again, I have more than 25, and if you don't know which one to use, just hover over and read which one would be best for your data set. And then for normalization here, we want to use equalize fluxes. You can uncheck generate rejection maps. You can minimize that. And then you can keep everything else the same. And let's apply global. Alright, so we have our calibrated master flat HA file. Let's take a peek at it. Wow, look at that. Okay, let's save it. File, save as, under our PixInsight folder, master. So let's call this one master flat HA. Look at that, super creative. Anyways, okay. Now let's do the same thing for O3 and S2. So clear out the HA files and add in the calibrated O3 files. So again, under the PixInsight image calibration flats O3, let's load all these babies in. So let's double check to make sure they are all O3 because they should be designated with a 6, because in my filter wheel, that's what it is. Cool. I don't need to change anything, so let's apply global. Alright, so our O3, master O3 is done. So let's check it out. Look at that, look at all those little weird things. Okay, so let's save that file, save as, under master, let's call it master flat O3, save. Alright, now let's clear out the O3 calibrated flat files and add in the calibrated S2 files. So again, under PixInsight image calibration flats S2, let's highlight all of our calibrated S2 flat frames. Keep everything else the same. Let's just double check to make sure all of them are S2, which in my filter wheel is number 7. That's why it's denoted as 7 in the file name. And we are good to go. So press apply global. Alright, so our master S2 flat frame is ready to go. Let's take a peek at it. And looks good. So let's save it, file, save as. Okay, master, call it master flat S2. Alright, so now that we have all of our master flat files, our S2 here, our O3, and our HA, we are ready to calibrate our light frames. So let's go over and do that. Okay, so in our last and final step of calibration, step 5, we will be calibrating our light frames of the North American Nebula by their filter type, and we will be using the image calibration process for this. So I have it open here, but if you don't, just come up here to process, all processes, down here to image calibration, and just click on this guy right here. So I have reset it, just reset it again, it's just for good measure. Again, so let's add in our HA light files. So let's go to add files, and we will go to lights, HA. Here are all of my approved HA light frames, so let's open those up. So we're just going to want to make sure that these are all HA files, number 5 in my filter wheel for me, so let's see. Alright, good. So we can disable the CFA portion of that because we're not using one-shot color camera. Formal hints, keep the same. Just like we needed to do for our calibrated flat frames, we need to create an output directory for our calibrated light frames, so let's go ahead and create that. So under PixInsight, come over here to image calibration, and we're not gonna put our calibrated lights under the flats folder. We're gonna create a new folder and call it lights. Create new folder and call this HA, and then press open. And just like our calibrated flat frames, the names of the files are going to have an _C at the end of them after they are calibrated. You can keep the signal evaluation the same, noise evaluation the same, input pedestal the same, overscan keep unchecked, master bias, make sure that's deselected. So for our master dark, we are going to be using our master dark of 300 seconds. So yes, make sure that it is enabled with the check mark, and let's add in our 300 second master dark here, not the master dark flat, but the master dark. So master dark 300 seconds. Cool. You can leave calibrate unchecked, and you can leave optimize unchecked as well. You can leave optimize unchecked, but you can check optimize if, for instance, your master dark is of a longer exposure than your light frames that you're trying to calibrate. You can just select optimize, and it will optimize your light frames for that. So for our master flat, we are going to add the corresponding master flat document or file. So here's our master flat HA file right here, and make sure that calibrate is unchecked, and everything else should be good to go. So just select apply global. Alright, so our HA light frames have been calibrated, and now we can move on to our O3 frames. So let's clear out the HA files, add files. Let's go over to lights, O3. So we don't want anything from our discard file or discard folder. We just want the ones that we kept as approved. Select open, and we need to change and create our output directory for our calibrated O3 files. So under PixInsight, image calibration, lights, let's go ahead and create a new folder for our calibrated O3 lights. I'm gonna call it O3, if you can believe that. Just kidding, guys. All right, open. Keep everything else the same. You can keep the master dark the same because we're not using a master dark flat. We're not going to use any of those, so make sure it is the master dark 300 seconds. We are, however, going to change the master flat file to the master flat O3 file. So come over here to PixInsight, master, and then find the master flat O3 file, and add that baby in. And oh wait, let's make sure that we have all O3s. So O3 in my filter wheel is number 6 in the position. So 6, 6, 6, 6, good. All right, apply global. All right, so our O3 lights have been calibrated. Let's go ahead and do our S2s. So let's clear out our O3s and add in those S2s. Again, we don't want anything from the discard file or folder. I don't know why I keep getting this mixed up. Okay, so again, we need to change the output directory, and we need to create an S2 output directory. So under PixInsight, image calibration, lights, let's go ahead and create that S2 folder. Create, open. Before I move on, let me just make sure that all of these are S2, denoted by the 7 for the 7th position in my filter wheel. Good. Again, keep the same master dark, the 300 second master dark. And the master flat, we of course need to change to the master S2 flat. So under PixInsight, master flat S2, open, and apply global. Alright, so we are done calibrating our light files, and we are done with the calibration process in general. So now we will move on to cosmetic correction. Alright, so now that our light frames have been calibrated, they ideally should be free of dust motes and vignetting, and the light frames should be looking good. However, sometimes unwanted artifacts may still be lurking around after calibration, like hot pixels, which show up as white pixels. That's because, unlike thermal noise, hot pixels are nonlinear, and because of this, they occur more randomly and are more difficult to eliminate. This is especially true for CCD cameras, but they do still show up in CMOS cameras. So cosmetic correction can correct for hot pixels as well as cold pixels, which are harder to visually detect because they show up as black pixels, and that's because they are essentially dead pixels. Alright, so let's just come up here to all processes, cosmetic correction, and just get this open up. So it looks like this. So how cosmetic correction is going to work is that it takes a problematic pixel and it will modify it by replacing its value with the average value of the pixels surrounding it. I know that some CCD cameras also may have some weird vertical column defects, which cosmetic correction can also account for. I don't have that problem with my ASI 2600mm Pro, but just wanted to note that. So yeah, it is important to cosmetically correct for these issues, or else these problems will just persist and cause even greater issues with the image registration process and beyond. So this is cosmetic correction, and so for organizational purposes, I'm going to load in my files by filter type, but hypothetically, you could cosmetically correct all of your calibrated light files together, regardless of filter type. Just be sure that they all have the same exposure length, because we will be using the master dark to help us with this process. So here, let's load in all of my calibrated hydrogen alpha files. So under PixInsight, image calibration, lights, HA. So here are all of my calibrated HA light files of the North American Nebula. I'm going to highlight them all. I'm going to open them up. And just like we did for our calibration frames, we need to create an output directory for our cosmetically corrected files. And this is again why I am cosmetically correcting them by filter type, not for any other reason. So under that PixInsight folder, I'm going to create a cosmetic correction folder. So I'm gonna add in another folder called HA, select open. So what you will notice in your images as file names now is that they are not only calibrated, but they are also cosmetically corrected. So you will also see a _cc as well as that _c. So just remember that cosmetic correction comes after calibration. So we are going to be using a master dark to help us out here. Let's load in our 300-second master dark. So here that is. Again, it's a 300-second master dark. It's not the master dark flats. We don't use the master dark flats for anything anymore. Beautiful. Let's enable the hot pixels and the cold pixels. I keep everything as the same. Seems to work for me. You can mess around with the parameters if you need to. I am going to enable auto detect and the hot sigma and cold sigma. I'm not going to use a defect list. I just don't really have any issues. So let's apply global now. Okay, so cosmetic correction for HA light files are good to go. So let's move on to O3. Let's clear that out. Add files. Again, we are adding the calibrated O3 lights. So under PixInsight, image calibration, lights, O3. Let's add all of those in. Just make sure that those are all O3s. Cool. Now we also need to create an output folder for our O3 cosmetic corrected light files. So let's create one of those. So O3. Beautiful. You can keep everything else the same and just apply global. Alright, so our O3 light frames that have been calibrated are now cosmetically corrected. So let's move on to S2. So let's clear out our O3s and add our S2s in. So again, under PixInsight, image calibration, lights, S2. Add in our calibrated S2 frames, open. And just as we did with HA and O3, we need to create a folder for our cosmetically corrected S2s. So let's open that up, and then you can keep everything else the same. Alright, awesome. We are done cosmetically correcting our HA03 and S2 light frames that have already been calibrated. So let's move on to grading our images. Now that we have calibrated and cosmetically corrected our light frames for each filter type, we need to register those images or align them all, and then we will need to normalize them and then integrate them. But first we need to make sure that we only use the best subframes of the bunch for those next steps. So to determine this, we are going to be using the SubframeSelector process to measure, grade, weigh, and approve images. Now, yes, we did use blink as part 1 of our image evaluation process, but in that first part, we were only removing the subframes with very visually obvious defects like star trails and large bloated stars. With SubframeSelector, on the other hand, it's going to allow us to numerically evaluate aspects of our images that our eyes may not be as keen to observe or can't really see at all, and then be able to compare those images based on certain statistical variables and then assign weights to them. This is going to be important for determining a reference frame for our StarAlignment process, as well as for determining the best images to integrate for our local normalization process. We are also going to need to determine the best image from each filter type to be references for image integration, which is our final step. So let's go ahead and open up SubframeSelector, come up here to Process, All Processes, and down to SubframeSelector. Okay. So you get a lot of windows. Start with this one. This is going to allow us to input and output our subframes or our measured subframes. So let me just minimize that for a second. This is our measurements window. So the measurements is going to display the data of our measured subframes, and then we have our expressions window right here. Expressions is going to allow us to apply certain weighting criteria to our subframes for our image integration process and for us to approve and reject subframes based on certain criteria. So let me just minimize that as well. So first we'll begin with this window titled SubframeSelector, and we are going to be loading in our calibrated and cosmetically corrected light frames by filter. So let's start with the HA light frames. So come up here to Add Files, and make sure you are in the CosmeticCorrection folder. Let's go to HA, and let's highlight all of these. And you'll know that they have been calibrated and cosmetically corrected because of the _C right here and the _C right here as well. So let's open up all those. Just double check those are all HAs. Perfect. So let's come up here to Routine. Make sure that Measure Subframes is selected. It's the default, but just make sure that it is selected. Alright, so under System Parameters, we are going to input the subframe scale. The subframe scale is the image scale in arc seconds per pixel of your main imaging telescope and imaging camera. There are a few ways to get this information if you don't know it off the top of your head. You can, of course, just Google your telescope's focal length in millimeters, and you can also just Google your camera's pixel size as well if you don't know them. Or you can just open up an image from your imaging session. So I'll just open up this one, and just stretch it for you so you can see. Let's just come up here to File, down here to Fits Header. If your acquisition software configures Fits files and has these parameters indexed, then you'll be able to find the focal length and pixel size of your camera here in the Fits Header like this. So let's get the pixel size of the camera. So that's 3.76. And then the focal length of the telescope is 768.76, so let's just round that up to 768.8. I'm going to minimize that for now because we will come back and use it. So what I would do with that information, the pixel size and the telescope focal length, I would take 206.25 times parentheses pixel size of your camera, divided by the focal length of your telescope, and then close the parentheses. So for me, that's going to equal 1.007. So that equation would just look like 206.25 times 3.76 divided by 768.8. And again, yes, you get 1.007. So I would input that into here like this. Another way to do this is to use a website called astronomy.tools. Just open this up. It's a great website. Come over here to the field of view calculator, and we want to be in the imaging mode right here in the middle. So we are going to input our equipment. So I don't have a very common telescope or a very new one at that, so I'm just going to keep it at custom telescope because I know that it's not in that list. And then I'm just going to input the focal length on my own, so I know that it's 768.8 millimeters, and then the aperture, I know off the top of my head, is 110. Again, you can just Google these parameters. For camera, again, you can just create a custom camera and input the resolution, the pixel size, or if yours is in the drop-down menu, just select that. I think mine is, so I'm gonna look for that 2600 mm Pro. So we can use this one, and you see how it's updated the pixel size here. The next thing we need to do is add a object. So I'm just gonna come over here to Messier, and let's just do the Lagoon Nebula. Doesn't really matter. But what you're seeing here is the resolution of 1.01 and then Dawes limit 1.05. So you would want to select the 1.01 and just input that here. But I'm just going to keep it at 1.007. So for camera gain, let's open up that FITS header. Again, it's not referring to the gain that you used per se. It's referring to the electrons per ADU. So you can come under this FITS header again, and we can find the gain here, the E gain, the electronic gain. So for me, it's going to be 0.24. So I'm just input that at 0.24. And then my camera resolution is a 16-bit camera. The site local midnight, you can just keep it at 24 hours UTC. For scale unit, I keep it at arc seconds. And then for data unit, I like to use electrons. And then we can press apply global, and it will measure our subframes, and we will then go over to the measurements window once that's done. So SubframeSelector is done measuring our frames, and it is displaying the data in a listed view here at the top, as well as a graphical view down here in the measurements window. And so what we need to do now is we need to determine what makes a good frame versus what makes a bad frame. And we will need to weigh those frames for our image integration process. So image weighting is really important because it allows us to choose the metrics or the quality factors of an image that we want to concentrate on, and then optimize when we combine our images together to give us the best possible result. And image weighting is really important because the data in our images, those metrics are always changing. They're variable, they're not static. And what I mean by that is that the conditions we take our images in are not static. Some images are taken closer to the zenith, so less air that you're looking through. Some are taken closer to the horizon, so there's more air that you're looking through. That of course affects qualities of our images. Same with the phases of the moon from night to night, and how that light pollution differs and shows up in our images, as well as our sky conditions like clouds and no clouds. These things can affect our tracking and guiding, as well as the ambient temperature affecting our star sizes. There are a lot of things that affect image to image, and these are just a few of the variables that cause differences from one image to the next, and that's why weighting is so important. You want to make sure that you weigh your images based on the qualities that you do want. So what are we looking for? There are a few things we want to consider when we're thinking about this, and one parameter is how focused our stars are in an image. So the narrower our stars are, the more focused they are, right? And so what we use is we use the full width half maximum, or the FWHM right here, of a star as an indicator for this. So the smaller the full width half maximum, the smaller the star, the more in focused it is. So I have just moved the full width half maximum. It was over there somewhere, and I just brought it over to weight. So this one's really important. Another important parameter to consider is how circular our stars are, and this is referred to as the eccentricity of a star. And eccentricity of stars could indicate how well our tracking and guiding are. So I've also included eccentricity right here. Another important parameter is the amount of stars, or the amount of stars that were detected in a frame. So the more stars in a frame, this usually indicates better transparency of the sky. So here are the stars column right here, or here is the stars column. And another important parameter to consider is the PSF flux, which basically means the profile of a star. It's the point spread function of a star's flux, or the quality or the light from the star that's being emitted. And this is important because it helps to determine the transparency of the sky, among a lot of other things. I've also included the SNR, or the signal to noise ratio, as something that's really important to look at, so I've moved that over as well. But in sum, we have the full width half maximum, we have the eccentricity, the stars, and the PSF flux that are really important parameters to consider when you're weighting your images. So we are going to be using an expression. I like to incorporate the full width half maximum, the eccentricity, and the PSF flux in this expression. I used to use stars in place of PSF flux, but I found that PSF flux works better for my system. But if you find that stars works better than PSF flux, go ahead and use stars. So let's just minimize this for now. But actually, before we do that, just take a note that the weight column is all zeroed. All of them are zeros, and that's because none of these images have been applied with a weight yet, so we're going to do that now. So let's minimize that. We can minimize that as well, and let's open up the expressions window. So I'm going to add in an expression here. The expression is one that I did not write, but I will add it down in the description box below for you. So we're going to concentrate on this first part here, and what this basically means is param, or parameter, minus parameter minimum is the first part of the expression divided by the parameter maximum minus the parameter minimum, which gives us a percentage for the given parameter. So in this case, the first parameter is for the full width half maximum. I also have a 1 minus here, and the reason I have that is because for the full width half maximum, a smaller value or a lower value is better. And then, so for this 20, 20 is the weight that the parameter will be given in the total weighting expression. So this is the full width half maximum portion of the expression, and so we also have eccentricity, and just like full width half maximum, the smaller the value, the better, so that's why we have a 1 minus, and I've also given it a weighting criteria of 20 for the total weighting expression. And then for PSF flux, again, here's where you can sub it for stars if you find that that works better, but PSF flux works better for me. I've also given it a 20 weighted expression, but you'll notice that I did not add a 1 minus. That's because for PSF flux, just like for stars, the larger the value, the better. It's not like full width half maximum or eccentricity where the lower the value, the better. So that's why there is not a 1 minus. And so the last portion is this 40, and that's because we want our total weighted expression to calculate to, or come to 100. So 20 plus 20 plus 20 equals 60. So 60 plus 40 equals 100. You can mess around with these parameters. You can add different parameters. You could add different weighting, different weights to each parameter. Just see whatever works best for your system. So again, there are no weights applied, but when I execute this expression, we now have weights applied to our images. Next, we need to approve and or reject our remaining subframes, and then output the ones we approve to be used in the next steps of our workflow. So I like to do this by looking at a couple of parameters. For one, I like to look at the full width half maximum. So let's come over here to the SubframeSelector measurements window, and under the measurements graph, I'm going to change this parameter to full width half maximum, so that FWHM. So what this graph is representing is the full width half maximum on the y-axis here with the values 2.6 to 3.5 and above. And then on the x-axis you have index, which represents the image that corresponds to the index number here. So the index number 1 is corresponding to image number 4. So if I come over here to indexed image number 1, it's right here, and you can see the full width half maximum is 3.379. And then over here you have the weight, which represents this line, or this dashed line. So for image index number 1, you can see the full width half maximum is 3.379, and the weight is 54.35, which you can see down here corresponds to that number here. So this black line here is the median, and then this dark gray area here and here above the median and below the median line represents 1 standard deviation away from that black line. And then this lighter gray area you see right here and here below and above the black line represents 2 standard deviation points away from the median. And so typically with full width half maximum for my system, regardless of the filter, anything that is above 4.0 is going to be bad. And so again, remember, for full width half maximum, values that are larger are not good. So I'm looking for anything that has a full width half maximum that is greater than 2 standard deviation points away from the median. And so here you don't see any images that have a full width half maximum 2 standard deviation points away from the median or above the median. So I'm not going to reject anything. I'm going to approve everything for now. But then I'm going to change the full width half maximum and look at the images using PSF Flux and its weighted distribution. And so just as a quick reminder, for PSF Flux, unlike full width half maximum and eccentricity, a lower value is going to be worse for PSF Flux, as well as for stars. So anything that is above two standard deviation points, I'm not concerned about, but anything below 2 standard deviation points away from the median, I'm going to reject. So in this case, and again, this lighter gray area represents 2 standard deviations away from this median here. So it looks like indexed image number 3 and then indexed image number 4 are both images that have PSF fluxes that are below 2 standard deviations. So I'm going to mark those for rejection or deletion. So I'm just going to click, and then you're going to see this circle around the image, the indexed image point here with the little X. And I'm going to do the same for indexed image number 4. And so you'll see up here in the listed view is that indexed image number 3 and number 4 now have red X's next to them instead of the green check marks. And as you guys can probably infer, the red checks or the red X's means that they're going to be deleted or removed from the bunch, and then the approved ones are going to be the green check marked. So I am going to keep all of the remaining 20 images. I'm going to show you another way to approve images with an approval expression. And so what I like to do with this approval expression, I like to use this expression when I am being a little bit more critical of the images, or if I'm using this instead of blink, because say for instance I just have hundreds of subframes and it's just a lot to get through, I might use this in the first portion of my image evaluation. So this will be a little bit more intense, but basically what this expression means is that it's going to exclude any subframe for which any of these relevant metrics here are much worse than normal. So anything more than 2 standard deviations worse than the median. So just note that you have to be careful when using greater than or less than, depending on whether the metric is goodness or badness. But typically bad frames, for example, due to passing clouds or poor tracking, are gonna fail several, if not all of these tests. So as a result, when I do use this expression, I usually tend to keep anywhere between 3/4 of my subs or less, but you are ensuring that you're excluding any poorly focused or tracked or cloudy images. But again, this is something that is a little intense, and it's used when I'm being very critical of my images or when I have a lot of images to get through. So I'm not going to apply that now, but that's just for reference, and I have given the expression down below if you would care to use that. So again, we are going to be approving 20 out of the 22, and so now we need to output our approved subframes into a new output directory. So let's come over to the SubframeSelector window, and then up here at routine, we're going to change this to output subframes, and then we're going to come down here to directory, and we're going to create a new directory for our approved images for SubframeSelector. So under that PixInsight larger folder here, I'm going to select that and create a new folder called SubframeSelector. You can call it whatever you would like, but we're basically putting all of our approved images in here. So I'm going to create a new folder for our HA light frames that have been approved, and I'm going to select open. And what you're going to notice, the postfix that's going to be added to the file names will be an _A. So the file names will now have an _C for calibrated, and then an _CC for cosmetically corrected, as well as an _A for approval. And then for keyword, I'm going to keep this as SS weight. We're going to be using this keyword in the image integration process. So the weights we did apply are going to be used in the image integration process, and I will show you where to use that keyword when we get to that section. So I'm going to use SS weight, but you can use whatever. Just make sure you do remember whatever that keyword is. So let's apply global. Alright, so our approved HA light frames are finished being outputted to the new file directory. So here they are, and you'll notice they have an _A applied to them as a postfix. So the next thing that we're going to do is we are going to select the best image to be used as a reference image in the image integration process, and then we will select the top 30% of our images to be used in the local normalization process. So let's go ahead and go back to the measurements window. We can minimize that for now, open up measurements, and I'm going to change the index to weight, and then from ascending I'm going to change it to descending. And so what you're going to notice is that the images with the highest amount of weight are going to be listed first. So I am going to select number 19 or indexed image number 16 as the reference image for HA during our image integration process. So a good way to identify that or to keep notes of it is just to create some sort of text edit file or some sort of note file or notepad file if you're on a PC. And just create something like this to just reference so that we can kind of keep track of all of our images. So I need to pick out the best image as a reference image for the HA master light during image integration. So again, that was image number 19 from June 16th, 2022. So what I'm going to do is I'm going to list that here. So it was 0019 on the date of 2022, 6/16. And so I will refer back to this document when I am using the image integration process. And the next thing I need to do is I need to identify the top 30% of my HA light frames for local normalization. So to do that, I'm going to just come back over to this window here, and I'm going to select the top 6 because 30% of 20 is 6. So I'm just going to do this off screen, but I'll show you it once I'm done typing it in. Alright, so I have finished typing those out, so here we go. I have my top 30% right here. So I'm going to refer to this document when I get to these processes later on in the workflow. So let's move on to our O3 images. So I can minimize this, and I can come over here to SubframeSelector, and I can clear. Make sure that the routine is changed to measure subframes, and let's add in our O3 files. So under CosmeticCorrection, I want my O3 files. Let's select all of these. And I'm going to keep everything else the same here. And then we'll come back to the output file directory for O3. We'll create one of those. But for now, we just want to measure our subframes. So let's do apply global. Okay, so we have our O3s loaded up here, and the weighted expression has already been applied to this data set. So that's good. Let's go back to measurements. So what we're going to do is we're going to look at the full width half maximum down here, change that back if you haven't already. And so what we're looking at is we're looking to find images with a full width half maximum that is above 2 standard deviations away from the median, which is this black line right here. And so anything above this lighter gray area is going to indicate that there is a full width half maximum that is greater than 2 standard deviations. And so I'm going to mark any of those images for deletion. So I'm going to remove, or I'm going to reject indexed image number 6, and you should see that here. And fortunately, that was the image that had the smallest amount of weight applied, which is good. And it looks like those are the only, or it looks like that is the only image for full width half maximum that has 2 standard deviation points from the median full width half maximum values. So let's go to PSF Flux. Oop, not that. So let's go to PSF Flux. So for PSF Flux, there looks to be like there are a few images that have lower PSF Flux values. So I'm going to be removing index image number 1, as well as index image number 2, as well as index image number 3. So I am approving 23 images out of the 26 images. So I'm going to minimize this for now, and I'm going to change the routine here to output subframes. And then I'm going to come over here, and I'm going to create a new file directory for our approved O3 images. So let's create one for O3. Okay, and then select open, and then press apply global. And of course, make sure that the SS weight is applied. So our approved O3 images have been outputted here, and you can see that with the _A postfix. And so the next thing we'll do is identify the best O3 image from the approved images to be used as a reference image for image integration, as well as the top 30% of our images for local normalization. Alright, so we have all of those images listed here. So let's move on to our S2s. And let's open up SubframeSelector here and change the routine to measure subframes. Let's clear out the O3s and add our S2s in. So under CosmeticCorrection, S2, add all those in. Make sure they are all S2s, indicated by the 7. Keep everything here the same. We'll come back to change the output file once we are done measuring. So let's apply global. All right, let's take a peek. Let's change this down back to full width half maximum. And the weight has already been applied. So again, with full width half maximum, anything that has a value that is above 2 standard deviations away from this mean, I want to mark for rejection. So it looks like index image number 5 has a value or FWHM value of 5.210, so we don't want that. And then index image number 6 looks to have a full width half maximum that is 4.1, so we don't want that. We also don't want index image number 7. Alright, so I'm just going to be getting rid of those ones for now. So then let's change it over to PSF Flux. And so for PSF Flux, doesn't look like there are any images we need to get rid of. So I am just rejecting 3 images, index image number 6, 7, and 5. So I'm just going to minimize that for now. Well, I can minimize that. And I'm going to change the routine to output subframes, and then I'm going to output those approved subframes. Under the SubframeSelector folder, let's create an S2 folder, and let's output them now. Okay, so let's check those out now. Bring this over here. So here are our approved S2 frames. So we need to identify the best frame for our image integration process, as well as the top 30 for, or the top 30% for local normalization. So let's go over here, open up subframe measurements again, and the top image is going to be number 14 from June 17th. So I'm just going to add it here, so give me a moment. Alright, and then the top 30% is going to mean 6 images, because 30% of 21 is about 6. So let's do that really quick. Alright, so we have, it's going to be 14, 10, 12, 2, 3, and 15. So let me write that over down here, so just give me a second. Alright, so we have our best images for each filter, and then we have our top 30% of images by filter type as well. And so next we need to determine what the best overall frame is going to be for StarAlignment. I typically use the best HA, so I'm just going to use 0019 for that. And then after this we can move over to StarAlignment. So at this point we have calibrated, cosmetically corrected, and graded our light frames of the North American Nebula. Next we need to align our images to ensure that the images are oriented in the same position for the integration portion. And so like I mentioned in the last portion of SubframeSelector, we needed a reference image to be used as the image that all the other light frames are going to be oriented to. So I'm going to open that up really quick. So just come over here and open up a File Explorer window, and then we have this as well. So that image was, let me write this, HA number 19 from June 16th. So I'm going to go to the HA images that were approved and find 19 from that date, and I am just going to open it. I'll just give you a peek here. Alright, so let's go up here to Process, All Processes, down here to StarAlignment. Right here. I don't know why I couldn't see it. So it looks like this. So this reference image, we're going to be using it here. So keep it at view and then click on this drop down, or click on this upside down triangle and then select this reference image here. And you want to keep everything here the same for now. And so the next thing I'm going to do is I'm going to load in all of my HA approved files. I could load in all of my approved files regardless of filter type, but I'm not going to do that just purely for organizational purposes. So I'm going to load in those HA files now. So let's go to SubframeSelector, HA, and load in all the HA files that have been approved. And let's just double check those are all HAs. And the reason I was saying for organizational purposes is because we need to create another output directory. So let's create that now by clicking on that little folder menu or folder icon. And we are actually going to create a new folder under PixInsight, and we're going to call this StarAlignment, create, and then under that one, let's create one for HA. And that way we have all of our registered images there. And so the postfix that our file names will have is the _R. And I think other than that, for star detection, you can keep that with the default settings, as well as star matching and interpolation as well. And so just apply global. All right, so our HA files have been registered, so we can take a peek at them over here. And so what you'll notice under the HA StarAlignment folder is that, yes, the image has an _R, but there is a corresponding XDRZ file, and that's because we generated Drizzle files, and we are going to be using those Drizzle files for image integration as well as for DrizzleIntegration. So let's move on to O3 and S2. And so I'm going to keep the reference image the same because that was the best image out of all of them. So let's clear out the HAs and then add in our approved O3 files. So under SubframeSelector, O3, select all of these. And then we want to change that output directory for the images to StarAlignment, or to our StarAlignment folder. Create a folder for O3, open, and we are good to go. Let me just double check. All right, press apply global. Okay, our O3s are done, and we can take a peek at them over in the StarAlignment folder. So here they are with the corresponding Drizzle files as well. So let's move on to S2. We can clear out the O3s and add in the approved S2 files. S2 under SubframeSelector, S2. Take in all of these images. Let's change the output directory for our S2 files. And under StarAlignment, let's create a new folder called S2. Select open. Let me just make sure these are all S2s. All right, and then press apply global. Okay, so all of our images have been registered, and now we are going to move on to local normalization. Alright, so we are done with StarAlignment, and we need to normalize our registered light frames by filter type. Now the reason we need to normalize our images is because our images may very well have different brightness levels on both the individual level and as a group. And what I mean by that is that even in some individual images, you may notice that an image is brighter in one or more parts of the image and darker in the other areas. So what we want to do is we want to normalize those brightness levels so that they are even across each pixel of the image. Now we also want the images as a whole to have the same brightness levels, and they may very well not, especially if we're taking images of the same filter type across different nights where there may have been more or less light pollution depending on the phase of the moon, or even what time of night you image certain frames and how close the target was to the zenith versus the horizon. So overall, we want to make sure that the average background brightness for our images by filter type is the same. And we will be using the local normalization process for this. So let's go ahead and open that up. So come up here to process, all processes, and down here to local normalization. It is right here, and it's gonna look like this. And so here is local normalization. It looks like this. And so how local normalization will work is that it will break each subframe up into small blocks of pixels, and then it will normalize them across the frames. And so to do this, we need to select a reference image for the other images to be referred to. And the best way to do this is to take the top rated images for a given filter type and then integrate them into a single image rather than just taking the single best image by filter type. You can, of course, do that, but statistically, you're going to have a better reference image if you take multiple great images and integrate them together and use that as the reference for normalization. And that's why we've identified the top 30% of our images by filter type during the SubframeSelector process. I am going to minimize this for now, and we are going to be using the image integration process for this. So let's reset that. And if you don't have image integration open, come up here to process, all processes, and then back down here to image integration, just like we used before. So just do a quick reset on that. And we are going to be adding in all of the images that we identified here for HA, all the top 30% of those. And so what you might notice is that under my StarAlignment folder, I have identified the best images with the little purple dot here. So if you have a Mac, you can do that by just tagging them with these colors. You can also do that on PC. You can just look up how to tag images with different flags and such, but this is just an easier way to do it. So I'm going to come over here to add files, and then under StarAlignment, under HA, I'm going to be selecting the images with the purple tag here. So that one, that one, that one, that one, that one, and that one. So we should have a total of 6. For image integration, keep the combination as average. That's always going to yield a integrated image with the highest signal to noise ratio. For normalization, do additive with scaling. And then for weights here, let's do the fits keyword that we created when we were outputting our images or approved images in SubframeSelector. So for me, that keyword was SS weight. Put in whatever your keyword was. And you want to make sure that the image, or you want to make sure that you have generate integrated image selected. Keep everything else here the same. Under pixel rejection 1, I'm going to be selecting percentile clipping, and that's because I only have 6 images. And then the normalization, do scale plus 0 offset. We don't want generate rejection maps, but you can keep everything else here the same. For pixel rejection, you can keep everything else the same here as well. And then for large scale pixel rejection, I'm not going to enable these, but if you do have several trails from airplanes or satellites or meteors, go ahead and use one of these. And so I'm just going to apply global. Alright, so it's done being integrated, so let's take a peek. Let's do a quick auto stretch, come over here and click on this guy right here. And it looks good. So I'm just going to title this HALN, and then I'm going to minimize the image integration. And then we can come back over here to local normalization. For reference image, just keep it selected at view, and then we want to select the HALN. Alright, and then for scale, I'm going to keep mine at 1024. This is referring to the pixels, and this really depends on the dimensions of your image as well as the complexity of your gradients. But typically, a scale of anywhere between 256 to 1024 pixels is going to be good for deep sky images, but just try out these different scales to see what works best for your setup. So 1024 for me. For apply normalization, do view execution only. You can keep no selected or no scale component deselected, as well as global location normalization deselected, but you do want to generate normalization data, so have that enabled, and you don't want this to be enabled down here, the show background models. For outlier rejection, you can keep everything down here the same. And then scale evaluation, for method, I'm going to keep it at PSF flux evaluation and keep everything else down here the same. So let's load in our HA star aligned images. We want to select them all. Let's bring those in, make sure they are all HA. It's really important for local normalization. And then now we need to create a new output directory for our local normalization data that it's going to be generated. So under PixInsight, let's create a new folder called local normalization. And then under local normalization, create one for HA, or create a folder for HA, select open. And then the postfix that will be added to the file names will be _n. Press apply global. Alright, so our HA frames are done. We do have our HA local normalization files here. So let's move on to O3 and S2. So let's just delete this, say yes. And we need to create our integrated image for O3. So let's clear out the HA data and add in the O3. And so what I did for O3 is the same thing I did for HA, where I just identified the images that needed to be normalized here with the purple little tag. So I'm going to come over to image integration, add files, and go to StarAlignment, O3, and I'm just going to select the images with the purple tag. Alright, then open. So there are 7, all O3s, and you can keep everything else the same and press apply global. All right, looks like O3 is ready. Let's take a peek at that with an auto stretch. Looks good. And so you might notice these black edges. That's fine. That's just from field rotation when we registered the images. So that's fine. We can just get rid of those in post with dynamic crop. So let's just change the identifier to O3 LN. You don't have to change the identifier, but I'm just doing that for this video. So we can minimize image integration. Let's open up local normalization again, and then change the view to O3 LN, and let's clear out those HA files, and then bring in our registered O3 files. And then you will want to create a directory for the local normalization data to be stored. So under local normalization, let's create a folder for O3. Open, and then press apply global. Alright, so our O3 data is done being processed, and we can move on to S2. So let's just minimize local normalization for now, and we can delete this O3. So let's open up image integration, and then we can clear out the O3 images and add in our S2 reference images. So again, I'm going to be selecting all of these images for S2, and I have identified them with the purple little tags here. So under StarAlignment S2, let's select this one, this one, this one, this one, this one, this one, and that will be it. So 6 images for S2, and we are good to go. So press apply global. Alright, so that's done. Let's take a peek at that with a quick auto stretch. Looks good. Okay, I'm just changing the identifier just for this video, but technically you don't have to. I'm just going to keep that open. So close image integration or minimize it, open up local normalization, and change the view to S2 LN. And we want to clear out all the O3 files and add in our S2 files under StarAlignment. So here's S2. Open those up. And then we do want to create a new file directory for our local normalization to go to. So under local normalization, create a new folder called S2 and select open. Just make sure these are all 7s or S2s and apply global. So we have made it to our last 2 stages of the pre-processing workflow. The step after this is going to be optional. It's called DrizzleIntegration, but after this step right here for image integration, we will have 3 master light files that you can walk away with, which is great, or you can stick around for DrizzleIntegration. So we are going to be improving our signal to noise ratio by integrating all of the files together by filter type, and we're going to be using image integration like I said. So let's go up here to process, all processes, down here to image integration. If you don't already have it on the side like I do, it's going to look like this, and we want to press reset. So let's add our HA files in. So we are going to be using our files from StarAlignment. So HA, add all these in, and the reference image that we need to select is reference number or image number 19. So let's go over here and find that. It looks like it's right here. So I'm going to set it as a reference by selecting this button, and you're going to see it listed as number 1 now, which is good. And then what we need to do, we need to add the drizzle files in. So let's add our drizzle files in that we created in the StarAlignment process. So again, they're going to be under StarAlignment as well, and they're going to be listed as the XDRZ files. So go ahead and select all of those. All right, and then the next thing we need to do is add our local normalization files that we generated in the last part of our workflow. So come over here to PixInsight, local normalization, HA, and add in all of these files. Cool, so let's just double check to make sure these are all HA. They are. So I have a total of 20 for formal hints. You can keep that the same. For image integration, Combination, keep it at average. Normalization should have automatically been populated when you added your local normalization files, so that's what we're going to be using. For weights here, we're going to be using our weight keyword that we created during the SubframeSelector process, so let's change that to fits keyword, and then for me, it was SS weight, which is the default. And then we are going to be generating an integrated image, so make sure that is selected, and then make sure that generate drizzle data is also selected, and then keep everything else the same. For pixel rejection algorithm, since I have 20, I'm going to be selecting linear fit clipping. You can hover over here and just see which option would be best for you based off of the number of subframes in your data set. So linear fit clipping for me. For normalization, it's going to be local normalization again. We don't want any rejection maps, so let's deselect that, but you can keep everything here the same. And then for pixel rejection 2, I'm going to keep everything here at the default. And then for large scale pixel rejection, I'm going to enable these because I did have some airplane trails and satellite trails. So I'm just going to keep those enabled, and I'm just keep the values the same. And then for signal and noise evaluation, I will keep the default settings as well. And so now we can apply global, and we will have our final master light file for HA. Alright, so our HA master light file is done being integrated. Let's take a peek at it. Come over here to auto stretch it, clicking on this guy right here, and voila, look at that. It is a beauty. Lots of great detail. So let's save it up here at File, Save As, under PixInsight. Come over here to Master. We're going to call this Master _ light HA 300 seconds. And then make sure it's an XISF file. Select Save and make sure it's a 32-bit floating point file. Select OK. And I am just going to close this out for now so my PixInsight doesn't crash, but I will open it up at the end. So let's move on to O3. So under ImageIntegration, clear out our HA files, and then add our O3 files from StarAlignment. So go to O3, select all of these, and we needed to select our reference image. So for O3, our reference image is going to be number 19, or sorry, number 1. So I know that it was the second one. It was this one right here. Okay, so set reference, and then let's add our drizzle files in. So again, under StarAlignment O3, select our drizzle files that were generated, and then let's add our local normalization files for O3. So under local normalization, PixInsight local normalization O3, add all of these files in. Perfect, so we have our reference image here, then we have our drizzle files in there, as well as our local normalization files. And we can keep everything else the same because we have a total of 23 files, and the weight keyword is also the same that we used, and the rejection algorithm is going to be good for data set for 23 subframes. So press apply global. Okay, so our O3 master light file is ready to be reviewed. So let's give it a quick auto stretch. And voila! Looks great. So let's go ahead and save that. File, Save As. We're going to save it under Master. We're going to call it Master Light 03. XISF file, save, 32-bit. Okay. I'm going to close this out for now. Alright, so we can start with S2. I've cleared out the O3 frames. Let's go to Add Files. So under StarAlignment, S2, let's bring in those files right now. Oop, I don't know if I got them all. Okay. Good, now let's select our reference frame. So our reference frame, again, was number 14 from June 17th. So let's find that one now. Okay, it's right here. So I'm going to set that as our reference. And then we are going to add our drizzle files in. Again, our drizzle files were generated when we did the StarAlignment process. So under StarAlignment, S2, select all of these files, bring those in, and then you'll see this little D here, and then add the local normalization files that we generated in the last step of our workflow. So under local normalization, S2, here, all those files, and then you should see that N. So we have our reference frame selected with our normalization files as well as our drizzle files, and they are all S2, and we have a total of 21 images, so we can keep the rejection algorithm at linear fit clipping. And let's apply global. Alright, our S2 master light file is ready to be reviewed, so let's take a peek at that and use an auto stretch. Yay! Looks great. Alright, let's go ahead and save this. Under File, Save As, PixInsight, Master Light, S2, 300 seconds, XISF file down here, select Save, and then you want it to be a 32-bit floating point image. Press OK, and we are good to go. So let me close this out, and then now we are going to move into DrizzleIntegration. Alright, so we have our 3 master light files for HA, O3, and S2 of the North American Nebula, and now next we are going to move on to a optional step called DrizzleIntegration, and DrizzleIntegration is really great to do, especially if you are going to be printing your images, and it just adds a lot of detail to your stars and your structures, so I highly recommend doing it, although I do recommend having anywhere between 30 to 60 images. I, however, don't. I only have about 20 images per filter, which is fine. I think like the minimum should be like 15 frames, so we're just gonna do it anyways. So let's go over to Process, All Processes, DrizzleIntegration, and it's gonna look like this. And so DrizzleIntegration, the files that are going to be outputted are gonna be like quadruple the size, but they are worth it in my opinion. So just like we did with ImageIntegration, where we just did it by filter type, let's do HA first. So let's go over to Add Files, and under StarAlignment, we are going to start with HA, and we are going to be bringing in those drizzle files once again. And then we need to add in our local normalization files that we generated as well. And so let's select those. So that should be good. Those are all HAs. Now for formal hints, you can keep that the same. For drizzle, make sure it's a scale of 2. That works best for my system. Same with the drop shrink. Just look those over, see what is best for your setup. The kernel function is going to be square. Make sure that the enable CFA drizzle is disabled. And then you want to keep everything else here the same. And let's apply global. Okay, so our master HA light file, drizzle file is complete. You can get rid of this drizzle weights image and just by clicking that. So let's take a peek at that. Come over here and give it an auto stretch. And ideally what DrizzleIntegration is going to be doing is it's going to be adding much more detail as you zoom in. So around the stars especially, you're going to see a lot more clarity, a lot more pixel density. And that's important if you're going to have your images printed. And it just gives a lot of good detail. So I'm very happy with this. So let's go ahead and save this. Let's go up here to File, Save As. Under PixInsight Master, let's call this Master Drizzle Light HA, 300 seconds. Okay, let's close that out for now, and then let's move on to O3 and S2. So we can clear out our HA files and bring in the O3. So we want our images from the StarAlignment process. So under O3, let's select all of these drizzle files for our O3 images, and add our local normalization images. or files rather. Oh, nope, under 03. All right. Good. All right, let's press apply global. All right, so we are done integrating our O3. We can close out these drizzle weights and let's take a peek. All right, looks really good. Yeah, I'm very happy. Okay, let's go ahead and save this, and then we can move on to S2. So master, we're gonna call this master drizzle light 03. Save that as an XISF file, 32-bit, press OK. Alright, our S2 is done. We can get rid of this drizzle weights image and let's take a peek at the S2. Awesome. Alright, so we are done with that. Let's just go ahead and save it. File, save as. Under PixInsight master, let's call this S2. Okay. So here are our 3 master drizzle light files with HA right here, O3 right here, and S2. I did crop and rotate these to get to the final image, but yeah, thank you all so much for sticking with me. I know this is quite a bit of a long process, but I think it's well worth knowing how to do this. So if you like this video, please consider giving it a like and subscribing to my channel. I really appreciate all of your support, and until next time, clear skies!